Okay, so we are going to look at what are classically known as the famous elevator problems in physics. And basically, it's just thinking about how a free body diagram and a force analysis and acceleration and what that means and what the information you're given conceptually gives us the power to kind of make some deductive reasoning about motion and what an object is doing. All right, so let's imagine you are riding in an elevator and you're standing on a scale. Okay, so we all know when we're riding in an elevator, we have these like feelings of your tummy falls away or you feel really light or all those sorts of really heavy feelings as we ride into an elevator. So let's see what that actually looks like. So you imagine you're riding in an elevator and you hop on the elevator and you're on the 5th floor and you suddenly feel heavy. You look down at the scale and you realize your weight just went up. Okay, so your scale reads more than you know your weight to be. What direction are you headed? All right, let's see if we can't figure that out, or maybe we can't figure that out. So first of all, let's imagine what it means to be standing on a scale. Well, that's pretty easy to imagine. Here you are standing on a scale in an elevator. Now, I don't need to draw the elevator because you aren't actually interacting with the elevator. You are interacting with the scale and the earth. So there are only two forces acting on you in this situation. Physical interactions. You have the force of gravity, and that's between you and the earth. And we know the force of gravity always acts down. So if we were to draw a free body diagram, we know the force of gravity is acting down. And we know that's equal to the weight, which of course is mass times g for our situation. It's always m to mg. So that's your weight. That's your true weight, dependent on your mass and the force of gravity. All right, so that's your weight. The other thing that you're interacting with, of course, is the scale. And what's the scale doing? Well, it's pushing up on you, right? It's holding you up. You're pushing down on it, so it's pushing up on you. It only exists because you're making contact with it. So what do we call that force that exists by that contact, that squishing of molecules? Well, we called that a normal force. So the scale is actually the normal force in this situation, but it is indeed the force of the scale. And that's on you. So you and the scale, and that is acting in the upward direction. Now, before I draw that picture on the free body diagram, let's go back to revisit what we said we were experiencing. So you look down at the scale and you see that the scale reads more than your weight. So we know that the scale force is greater than the force of gravity. The scale reads more than your weight. That feeling that you feel, that's the feeling of the floor pushing up on you. Sorry, the scale pushing up on you. That's what we feel. And that feels different than when I'm normally standing on the scale. And so we feel heavy because that force is larger. Okay? So the arrow pointing up has to be greater than the force of gravity if the normal force is larger than the force of gravity. All right, now remember, this was, what direction are we heading is the ultimate question. Okay, so we know that the normal force is greater than the force of gravity. So what's the direction of the net force? Well, if I added these two together, the net force would be in the upward direction. Remember, the net force direction and the acceleration direction are the same. So the acceleration has to be in the upwards direction. Now, can I have an acceleration in the upwards direction? Sure. Under what situations? Well, remember that acceleration and direction of motion have some relationships that we've learned about. If my direction of motion and my direction of acceleration are in the same direction, then I'm speeding up. So, if my acceleration is upward, if I'm moving up and my acceleration is up, I'm speeding up. So So I could be moving in the upward direction on that elevator, and I would be speeding up. It'd be like I stepped into the elevator at the 5th floor, like I said, and I started to go in the upward direction. So that's one possibility of my direction of motion. Now, if I indeed just stepped into the elevator and I was looking at this situation immediately after stepping into the elevator, then one might say, that makes sense. I stepped into the elevator, my direction of motion is up. I would be speeding up at that point, just starting to ascend into the building, and so I'd be moving in the upward direction. Now, is that the only scenario that we feel when the normal force is larger than the force of gravity? Well, not so much. Remember, if I was moving in the downward direction and I was accelerating in the upward direction, I'd be slowing down. So if I was on the elevator approaching a floor in the downward direction, then in order for me to slow down, my acceleration would have to be in the upward direction. So to answer the question, which direction am I moving, I have to know a little bit more information. Because just because the normal force is greater than the force of gravity, that gives me two options, A and B, for that situation to pan out. So, in order for me to know what I'm doing, what direction I'm heading, I'd have to know, am I speeding up during that time or am I slowing down during that time? So if I was just getting on to the elevator like I presented at the beginning, I've just entered the elevator at the 5th floor and the motion of the elevator begins and I notice that the force of gravity is less than the normal force, then I must be moving in the upward direction. All right, let's try another one. Let's imagine that we are riding in an elevator. We woke up riding in an elevator. So I have no idea when I got on. I have no idea where I got on. And all I feel is light. So what direction am I moving? Okay, I feel light. If I feel light, that tells me that the normal force is less than the force of gravity. I look down at the elevator floor while I'm moving, and sure enough, the scale reads less than my weight. Okay, again, no idea how I got there. I just woke up moving in an elevator. So, same situation. Here I am, standing in the elevator, and the force of gravity is interacting with me between you and the earth. And we know that points down, and that is equal to my weight. And sure enough, the elevator is also interacting with me. The scale, is interacting with me. So I have the force of the scale, which we said was a normal force, and that's between you and the scale, and that's pushing up. Now we're told that the normal force is less than the force of gravity, so I'm going to draw that arrow shorter. If the normal force is less than the force of gravity, what's the sum of the forces? Well, the sum of the forces must be down. And if the sum of the forces is down, the acceleration is down, because the net acceleration is in the direction of the sum of the forces. So, when can the elevator be moving with a negative acceleration? Well, one situation is that it can be moving down and speeding up. If my direction of motion is in the downward direction and my acceleration is in the downward direction, then indeed I must be speeding up. Or I can be moving up and slowing down. If the direction of motion is opposite the direction of the acceleration, so if I'm moving up but my acceleration is down, then I'm slowing down. And so either of these two can happen, and if I don't know what the initial situation was to get me into a moving elevator, I can't distinguish between them. And indeed, we would not feel a direction of motion. It feels the same to be moving down and speeding up as it does to be moving up and slowing down. All right, let's try one more situation that's a little different bend to it. Let's imagine that you are in an elevator and you are speeding up. You're in an elevator and you are speeding up. You also know that you entered that elevator on the first floor. So you entered the elevator on the first floor and you started moving up and speeding up. What is the direction of, what does the scale read? More than your weight or less than your weight? So, speeding up and moving up. All right. Well, these are still the same two forces acting on us in the elevator. We have the force of the gravity and the force of the scale. Now, regardless of what I am doing in the elevator, the force of gravity is always my weight. That arrow is always the same, regardless of whether I'm moving up, down, speeding up, slowing down, constant velocity. So I'm told I'm moving up and speeding up. If I'm moving up and speeding up, this tells me that the velocity is positive, and if I'm speeding up, the acceleration is in the same direction, also positive. If the acceleration is positive, then the sum of the forces is positive. If the sum of the forces is positive, an only way to get a positive sum of forces is if my up arrow, representing the force of the scale, is larger than my down arrow. And so the scale reads more than my weight. So I can ask a variety of questions, always kind of going back to this idea of drawing a free body diagram, what forces are interacting, and then what does the motion tell me about the sum of the forces and the net force, and therefore the relative forces? Or what does the relative forces tell me about the motion, the acceleration that's happening? So going through those types of questions, what are the forces acting? What ones are steady? What is the object doing? What does that mean for my motion? Helps us to use conceptual ideas to talk about the classic elevator problems. Good job.